Today we're going to talk about marginal functions. Marginal functions is basically just a section that's full of applications. So you're not going to be learning any new derivative rules today. We're just going to be learning to apply these derivative rules to some derivative rules. We're going to be learning to apply these derivative rules to a new type of application, which is called marginal functions. So we're going to find and interpret marginal cost, average cost, revenue, and profit functions just using the rules we already have for derivatives. So here's how we're going to start this off. We're going to talk about how we would solve an application problem dealing with cost using information that we already know. And then we're going to kind of talk about how this leads us into the marginal function. So for your example, the daily cost of producing coffee pots is C of x equals 0.001 x cubed minus 0.03 x squared plus 60x plus 2500, where x is the number of pots produced. Find the actual cost in producing the 51st pot. Now, this is not asking you to do anything new that you've never seen before. You're just being asked to find the cost. Now, if we were to actually evaluate C of 51, because I think sometimes if you're not quite sure exactly what question you're answering, students tend to be like, I have this information, X is the number of pots, I've got a cost, and then they just find C of 51 because it seems like the thing to do. But it's really important to remember that C of 51 is the cost for producing 51 pots, but it's not the cost for producing the 51st pot. So in order to figure out that cost, what we can do is we can find C of 51 and find the cost for making the 51st pot. And then we'll take off the cost for the 50 pots that came before that. So see what I'm saying? Let's find C of 51. Now, C of 51 represents the cost to make 51 pots. Cost to make 51 pots. And we'll evaluate that in our calculator. So I'm going to get mine out here. Every time I switch calculators, I need to switch a setting. So give me a second here. It all depends on how much sunlight is coming into the room. All right, so I'm going to go ahead and take my function, 0.001. Now, if you'd like, well, I'll show you how to do this just using the regular part of your calculator. We'll just do 0.001 times 51 cubed minus 0.03 times 51 squared plus 60 times 51 plus 2500. And you come up with 56.14 and then about 62 cents. So I'm going to put that down here. So remember we did 0.001 times 51 cubed minus 0.03 times 51 squared plus 60 times 51 plus 2500. And this is about 5614.621. Now we're going to end up getting rid of that extra decimal place since we're talking about costs, but let's go ahead and just find C of 50 now. So C of 50 is the cost to make 50 pots. So we're going to do the same thing here, 0.001 times 50 cubed minus 0.03 times 50 plus 60 times 50 plus 2500. So I'm just going to go through. I'm going to hit a second and then entry or second enter, and it's just going to pull up my last formula. Everywhere I see 51, I'm going to replace it with 50. So there should be 3 places where we do that. Enter, and I get 55.50. So if I want to find the cost of producing just that 51st pot, what I can do is take C of 51, the cost for the first 50, take off or I'm sorry, the cost for the first 51, take off the cost for the first 50, and that will get you to the cost to produce the 51st pot. And you end up with 56, 14, 62 minus 55, 50 is 64, 62. So this would be the cost for making just that 51st pot. And hopefully, I feel like that should be at least somewhat intuitive to us, because if we think about C of 50, we're noticing that, you know, it costs a lot of money to make these 50 pots. So to make just one pot, you know, it makes sense that our value should be somewhere a lot less than that. But I mean, if you've ever gone shopping for a pot, you should maybe have some sense of how much they cost to buy. So I feel like that makes sense depending on what kind of pot you buy and where you get it. But that seems pretty reasonable to me. If you got something like 5,000, I'd be like, really, the cost to make one pot? And then you'd want to think about that, because if you just did C of 51 and you got 5,614, you'd be like, wait, is this the cost for producing one pot? I don't think so. But this seems a lot more reasonable. So think about that. So now what we're going to do is we're going to find and interpret C prime of 50. Not 51, C prime of 50. So in order to do that, we need to find C prime of X. So I'm going to take my C of X. I'm going to bring the exponent down, rewrite my variable, decrease the exponent by 1. And I'm going to do the same thing in the second term. In the third term, I'm just going to lop off that X, because the derivative of 60X is 60. And the derivative of 2,500 is 0, so I'm not going to write that one in. If you would like, you can simplify the C prime. There's not a whole lot you can do to it, but at least you can multiply. So I would say this is 0.003 x squared minus 0.03 times 2 is 0.006. I'm sorry, 0.06 x plus 60. So there's your derivative. Now, once you have your derivative, you can go ahead and evaluate it at 50. So we're now finding C prime of 50. So I can go ahead now and put this into my calculator as 0.003 times 50 squared minus 0.06 times 50 plus 60. And you end up with 64.5, which in terms of dollars and cents is 64.50. So the whole point in this example is to illustrate something. The actual cost of producing the 51st pot was 64.62. Remember that when we take a derivative, we're thinking about a rate of change in the cost. So when we take the derivative of our cost function C and we evaluated it at 50, what this is doing is it's giving us an estimate for the cost of the 51st pot. So we'll notice that C prime of 50 gives an estimate for the cost of the 51st pot. And that's what this entire section is going to be all about. Like, what if I wanted to make one more of something? How would that affect the cost? How would that affect the revenue? How would that affect the profit? And then we'll talk a little bit about how that relates to averages of all of those quantities as well. So that's the whole idea, finding the cost of making that next item. And if you're wondering, like, well, why would it matter? Wouldn't it cost the same to make the 51st versus the 21st? Well, not necessarily. I mean, if you're thinking especially about like fixed costs, if it costs you a whole bunch of money just to rent the facility in which to make all these pots, and you've got a certain number of employees, I mean, the cost to rent the facility is not going to go up as you make more and more and more pots. So on and so forth. So in a lot of instances, you'll find that the cost will probably go down for the 51st pot, and then maybe even the 61st pot. And then we'll probably even talk about at what point would that cost start to go up again. That's something that we would do more in the next chapter. But for a while, that cost would start to go down because now you're utilizing your resources to make more and more of that product, and you're becoming more efficient. And at some point, if you make too many pots, then your cost starts to go up again. Not always, but we'll kind of talk about how that relates to all this information. So marginal functions. Marginal cost, revenue, profit, etc. is the cost, revenue, profit, etc. of one additional unit. We know the derivative will give an estimate for the cost, revenue, profit, etc. of one additional unit. So to find the marginal cost, revenue, profit, etc. function, find the derivative of the cost, revenue, or profit function. That's it. So I know, I feel like sometimes I start an application section and students are like, no, this sounds so hard. We're really just going to be taking a lot of derivatives and just checking to make sure that what we're doing makes sense and that we fully understand what the question's asking. Don't make it out to be harder than it is. Marginal functions are not meant to crush you at all. All right, same example. The daily cost of producing coffee pots is, you're given the same function as you were previously. C of x is 0.001x cubed minus 0.03x squared plus 60x plus 2500. Find the marginal cost when x equals 200 and interpret the answer. So to find the marginal cost, you're just going to be taking the derivative at 200. So find the marginal cost when x equals 200. Well, that's how you're going to do it. So if you're being asked to find the marginal cost, find the derivative of the cost function and then evaluate it at that value of x. Now, we already found the derivative previously, so I'm going to use the derivative that we found earlier, and I'm just going to evaluate it this time at 200. So we found that c prime was this function, 0.003x squared, blah, blah, blah. You should have it up there at the top. So I'm going to enter that again. 003 times 200 squared. And then we had minus 0.06 times x. So we'll multiply that by 200 and then plus 60. Now this function should already be in your calculator because you just used it to evaluate 50. We can use it again just as it is if you want to do second entry, or you can just enter it again, which might be easier than going back and replacing your variable with different numbers or replacing the 50 with the 200. You can do that. It's up to you. 0.003 times 200 squared minus 0.06 times 200 plus 60. And I get 168. So this is interesting. If you're kind of like 168, that seems kind of odd because for producing 50 pots, we get that the cost for the 51st pot was $64.50. Well, this means that as they start to produce more and more pots, their production costs are going up. So at some point, you've kind of hit this place where you've produced enough. Maybe we should look at that real quick and determine where that point is. That might be really helpful to us. So we have $168. That means that this is the cost of the 201st pot. Is about $168. That is what that means. All right, sorry, I started to go off on a total tangent about that last example in the graph, and I decided, you know what, we're going to talk about this graph later because that one in particular doesn't really give us a lot of really good information. So we're not going to discuss the way the marginal cost is represented by that graph. But let's move on to the next example and talk about the average cost function. Now, you guys have spent some time finding averages. We always think about, if you're taking like the average cost of your dinner over the 4 people who ate the dinner, you divide it by 4. Well, whenever we're trying to find the averages, we just divide it by the number of units that are involved. So the average cost function gives the average cost of producing X units and is given by C bar of X. If you're not sure how to say that, it's C bar of X. If you all took stats, you should have seen that type of notation before with X bars. C bar of X is going to be the cost function divided by the number of units X, so cost per unit. Now we're going to use this in the next example. So we're going to let C of X be 150X plus 100,000 by the total yearly cost for producing, B, the total yearly cost for producing car stereos, B, the total yearly cost for producing car stereos. Find the average cost function. So to find the average cost function, we're just going to take our cost function and divide it by X. So C bar of X is going to be C of X over X, which means we're going to be taking our 150X plus 100,000 and dividing it by X. Now, if you look down, you'll notice that at some point we need to find C bar prime and the marginal average cost. So you might want to put this into a form that makes your derivative a little bit easier. For instance, I would split this up using the common denominator. This is the sort of technique we used in 3.1 when we talked about basic rules of differentiation. So we could just split this up as 150X over X plus 100,000 over X. And when we do that, the X's will cancel. You know what? I don't know what's happening to me today, but it's definitely Monday. And I don't know. I don't usually get this Monday thing. 150 plus, here, I'll write the whole version out. 150X over X plus 100,000 over X equals. And then in the first term, the X's will cancel and you just have 150. In the next term, you might want to write this X with a negative exponent because it's going to be a lot easier to take that derivative. Remember, we said that you could use the quotient rule on this, but why would you want to? 100,000 X to the negative first. So if all I asked you to do was find the average cost function, this first variation that we wrote would be completely fine. You could even take this derivative using the quotient rule, but I think this derivative would be a lot easier. Find and interpret C bar of 800. So for that, you might want to go back and use the initial since you're not taking the derivative here. So to find C bar of 800, I'm going to take 150 times 800 plus 100,000 divided by 800, and we'll get a quantity here for this. In the numerator, I have 150 times 800 plus 100,000 divided by 800. Make sure that your entire numerator has parentheses around it if you're going to be doing it all in one step like this. Otherwise, your calculator will just do the order of operations, and before it adds 100,000, it's going to take 100,000 and divide it by 800. It's very smart. It knows what it's doing. You end up with 275. And remember, that's average cost, so that's dollars. But don't just leave it. Anytime you have an application problem, you need a unit, which we just put on here, but you were also asked to interpret C bar of 800. So if we know that C bar is the cost, the 800 represents X, which was units. So in this case, we're talking about the units being car stereos. that means $250 per stereo would be the cost of production. So this means the cost of producing each stereo when 800 stereos are produced is $275. This means the cost per stereo, I'm trying to find a better way to say this. When 800 stereos are produced, is $275 per stereo. Okay, now that's going to change, of course, because that only assumes that you're producing 800 stereos. If you were to find the average cost at a different value, well, that would change. I mean, there are so many factors that would affect the cost of making each stereo. So if you're going to make 800 of them, the cost of producing each one would be $275. And of course, you could always evaluate this average cost using any other number of X, and you would see how that would change. And we'll sort of talk about, we'll talk a little bit more about this when we finish this one up. Find the marginal average cost function. So when you're being told to find the marginal of anything, that means derivative. Okay, so we're going to find the derivative of the average cost function. So we already know the average cost function. We found it up here. We wrote it specifically so that we could take its derivative. So what we're going to do now is we're going to use this last form of the average cost function and find its derivative. So this is C bar prime of X. Now, in this case, the derivative of your constant is 0. So one of those terms is going to pop off. And then you'll have plus 100,000. Bring the exponent down. Keep your X. Don't forget, when you take away 1 from the exponent, you're going more negative. You're not going up to 0, and it doesn't just disappear. -1 minus 1 is -2. So your marginal average cost is going to be -100,000. You can write it over X squared if you would like to do that. You might find that easier to evaluate for part D. Sometimes I just sort of look at what's heading my way next, and that sort of dictates the way I'm going to simplify my answer. I know in part D, I'm going to be interpreting this value, or I'm going to be evaluating C bar prime at a number. And personally, I feel like it's easier to evaluate an expression like this rather than leaving it with a negative exponent. But that's up to you. You can do it either way. But I'm going to let this be my C bar prime of X, my marginal average cost. Find and interpret C bar prime of 800. So we're going to take our derivative that we found previously. And everywhere we see X, we're going to plug in 800. So this is -100,000 divided by 800 squared. So -100,000 divided by 800 squared. Now, you don't actually have to have parentheses around the 800 in this case because your calculator is going to do order of operations. It knows to apply the exponent before it divides. So remember parentheses, exponents, multiplication, division, addition, subtraction. It's going to do the exponent first. When in doubt, use parentheses, but you don't actually need them in this case. You get -0.15625. And that might be one where you're kind of like, okay, cool, got the answer. And like, wait a second, what does that mean? Well, remember, we're talking about the average cost to produce each stereo. We were talking about when we produce 800 stereos. We now are bringing in this idea of the marginal average cost. So this is talking about how the cost per stereo is changing when we produce 800. And it's changing in a downward manner. Because it's negative, we know that that average cost per stereo is going to be decreasing. So we can say when we interpret this that the production of the 801st stereo Because remember, when we talk about marginal, we're always talking about making that next unit. The production of the 801st stereo will decrease the average cost per stereo by about, and then we can just think about this in terms of dollars and cents here. We'll just put a dollar sign on it. 15625, I guess, or about 16 cents. So what's interesting about this is you're noticing that you took the average marginal cost and you got a negative value. So that means that as you start to produce the 801st stereo, the average cost will decrease. The average cost of making each stereo decreases. But that kind of ties in with what we're going to be talking about in part E. Observe that the derivative of the average cost, this marginal average cost function, is actually always going to be a negative value. We got a negative value here, but think about the fact that the numerator is negative and we can only make a positive number of stereos. We can't make a negative. And even if we could, we're squaring the value in the denominator. When you take a number and you square it, it's always going to be positive. And when you take a number that's negative and you divide it by a number that's always positive, the quotient will always be negative. So C bar prime of x is going to be less than 0 for all x, which implies that as more stereos are produced, and this is kind of what we talked about in part D, the average cost per stereo will continue to decrease. And then that kind of leads us into thinking like, okay, well, if the average cost per stereo is just going to keep going down, eventually it's going to hit some limit. Well, think about your average cost function. When we're looking at our average cost function, looks like this, or it looks like this, or it looks like this. If you wanted to rewrite it again, you could rewrite it with a positive exponent in the denominator. I might even think that this variation of it looks better for answering the question in part F. This is the average cost function. Don't get it confused with your marginal cost. That was talking about the change in the average cost of production. But your average cost function is just saying what is the average cost, not what's the change in the average cost. In this case, as x continually gets larger and larger and larger and larger, this quantity is going to be impacting the average cost less and less and less. And as it continues to head off towards some value like infinity, let's say we're producing an infinite number of stereos, or we're at least trying to head to these super large values of x, this quotient is eventually going to find its way down to 0 because you're taking, yes, what's really a large number, but you're going to be dividing it by a number that's even larger. And this quantity or this quotient is going to end up eventually going down to 0. And all you're going to have left is the 150. So that's kind of the idea behind F. So the limit as x approaches infinity of C bar of x is 150. And that's because as x approaches infinity, this quotient, 100,000 over infinity, will go to 0. So I could say 100,000 over x will approach 0 as x approaches infinity. So this implies that as more stereos are produced, the average cost will approach $150 per stereo. average cost will approach, but never quite reach, $150 per stereo. So that is how average cost works. So if you see an application where it says find the average marginal cost, you're just taking that cost function and dividing it by X. And it's a really small little word that'll be in there, but you got to pay attention to it. So you're looking out for when it says, you know, find the cost function or find the average cost function. Usually you're given a cost function anyway. So find the average cost function means you're just taking your cost function and dividing it by X. So just look out for that word average. All right, so example 3. This one is a little bit trickier, but it kind of brings back this concept that we were talking about in, I believe it was 2.3 when we were talking about mathematical models. Suppose that the car stereos from example 2, suppose that the car stereos have a yearly total cost function. C of X equals 150X plus 100,000, so same function. And they have a demand equation, P equals negative 0.03X plus 600. Now, in this case, X is going to be the quantity and P is going to be the price. So this is going to be the price on this function. So we're sort of looking at this a little bit differently now. Instead of just talking about the cost and the average cost and how that's going to change based on production, we're going to use this idea that we have this varying price. So the price is going to vary based on demand for the product. And of course, that also relates back to the cost of producing the product. The revenue is going to be the number of units sold multiplied by the price. So revenue is going to be number of units times the price. And I think that should be intuitive to us as well. So sometimes I feel like I put this down and students are like, okay, whatever you say. But if you're trying to make money off of selling something, you're going to just take however many units you sold and multiply it by the price that you sold it for to figure out how much revenue you generated. It's that same idea. So R of X is going to be X times P. X is the number of units or the quantity, and P equals the price, which you were just told. Where often the cost is not fixed, but is related to X, which is the number of units by a demand equation P. So again, this is, oh, you know what? This should say price, not cost. So this is kind of like what we were just saying, or what I was just saying. The price is, of course, going to vary based on a lot of other factors, like the number of units and the demand. So we're going to use this information to answer a couple of questions. Find the revenue function. So you're being told already that the revenue is the number of units produced, which we know is just X units, multiplied by the price. And we were given that price is P, and we're given a function for P. So to find the revenue, we usually call that R of X. We're going to take the number of units, which is X. We don't actually have a number, so that's just going to be variable in this case. And we're going to multiply it by the price equation. And then we'll simplify it by distributing that value of X. So that's the revenue function. Find and interpret R prime of 4,000. Well, now you're being asked to find a derivative of a revenue. So once you know that, you know you're talking about that marginal revenue. So when we talk about marginal, we're talking about something having to do with the 4,000 first item. So let's go ahead and find that, and then we'll write down what it means. So we already know R. We're now going to find R prime. And then we'll evaluate it at 4,000. So R prime is going to be negative 0.03 And then you can just go ahead and multiply by 2. So 0.06x and then plus 600. Hopefully we're getting pretty good at taking these derivatives where we don't have to write every single thing. And then our prime of 4,000 just means we're going to take this, our prime function, and evaluate it at 4,000. So we have negative 0.06 times 4,000 plus 600, and we come up with 360. It's a revenue, so it's a dollar amount. To interpret this, this is talking about the revenue of the 4,000 first stereo. So the revenue from the 4,000 first stereo is $360. The revenue from the 4,000 first stereo is $360. Oh, per stereo. Okay. Find the profit function. Okay. So to find the profit function, remember anytime we're talking about profit, you're going to take how much money you generated, which is the revenue, and subtract off the cost that it cost you to make the item. So the profit function is the revenue minus the cost. We have a revenue function up here. It's negative 0.03x squared plus 600x. And then we're going to take away the cost function. Be very careful with this. I know I talk about it all the time, but make sure that when you subtract off this cost function, that you're taking off the whole thing, which means use parentheses. So it looks like that. So our cost function was given to us in the beginning. When you subtract it, you have to subtract the whole thing. So I'm going to rewrite this one more time, simplified. I only have one x squared term, so I'm going to leave that by itself right now. But I have 600x minus 150x, so that leaves us with 450x, and then we'll have minus 100,000. So that is your profit function. Now you're being asked to find and interpret the following. P prime of 4,000, which would be the profit of the 4,000 first stereo. If you know that you need to find P prime, we have a little bit of space up here. This is your profit function. We can go ahead and find its derivative up here since we have the space, and then we'll evaluate it down there. So P prime is negative 0.06x plus 450. Now we just need to evaluate that at 4,000 and at 8,000. So P prime of 4,000 is negative 0.06 times 4,000 plus 450. And then we'll do the same thing for 8,000. I'm just going to put this in my calculator. So I've got negative 0.06 times 4,000 plus 450. And I'm going to recall this again and do this for 8,000. Now at 4,000, we had 210, and at 8,000, we have negative 30. Okay, now these are in dollars. So since we have to interpret them, let's go ahead and do that. P prime of 4,000 would be the profit from the 4,000 first stereo. The profit from the 4,000 first stereo is $210, but P prime of 8,000 was negative 30. So that means it's not really a profit anymore, it's a loss. The loss from the 8,000 first stereo is $30. So if you knew this and you were the CEO of this company, you'd be like, "Ooh, like at this rate, I don't want to go make 8,000 stereos because I'm going to start losing money at that point." So the idea here is to figure out what would be like a really good optimal number of stereos to make in order to get the most profit out of them. So to do that, we'll graph the profit function and interpret it, and we'll find where the profit is maximized. So our profit function we found up here was, I'm just going to graph it in my calculator. Okay. So my profit function is negative 0.03 x squared plus 450x minus 100,000. Okay, I'm just going to graph that real quick in my standard zoom. And when I'm in my standard zoom, you'll see that it's not actually going to work for this problem, which is very typical. So what we're going to have to do in this case is get an idea of where we actually think this is going to occur, and then we can get a value for the maximum profit. Now, think about the fact that we already know that the change in the profit at 4,000 is positive, but when we get to 8,000, it's negative. So at some value between 4 and 8,000, we get this to change. So we definitely need to be looking at x between 4 and 8,000. Trying to find like the optimal, talking about optimizing things, and I can't find the optimal place to put my calculator, sorry. Okay, so I'm going to take my window. I guess I don't want to only look at it at 4 and 8,000. Okay, let's start at 0. We're going to go up to an x max of, let's say, 9,000. Okay, now this is a profit function. Our profits aren't getting like super high. The highest profit we found was $210. So let's say we go up to maybe, I don't know, 300. And we don't want to have a, well, maybe we do want to see negative profits because we are talking about losses here. Maybe negative 100 and see what happens. Window, what did I put in here funny? 9,000. Oh, I mixed up my X min and X max. There you go. Or my Y min and my Y max. Okay. All right, we should start to see this graph start to come down. No. Y, all right, negative 0.03 x squared plus 450x minus 100,000. I always have to check that first. So we had 4,000 stereos, 8,000 stereos, 100,000 was my y-intercept. So it's definitely coming down from there. 9,000. What if we just did like, we talked about 4,000 stereos. We talked about 8,000 stereos. Oh, I'm sorry, profit, negative. All right, so that's coming up from the negative values. My maximum should be occurring at 7,500. I know this already. Let's see. I'm not seeing it because maximum profit. Oh, I was looking at, you know why? Classic mistake. I'm looking at profit per stereo, not total profits. Guys, she's losing it. Oh. All right, so let's look at this with a larger value for the Y max. I mean, if you're looking at this graph, you're like, okay, clearly this is going up super high. How high is it going? Well, This needs to go a lot higher than it currently is. Let's see. Say we go up to 5,000. Way too low. Okay, window. 10,000. Way too low. 100,000. It's getting better. Window. 700,000. Oh. Graph the profit function and interpret the graph. 900,000. Better. Okay, so the thing is, my X values are going out to 8,000. I know that this starts to decrease somewhere before there, but I don't think we're high enough to see that decrease yet. So let's see. I'm also going to make this thicker because, no, that was as thick as it would go. Never mind. Window. 999,000. Better. Can we start to see it head downward? Nope. I'm going to need to increase my X maximum. 10,000? No. 19,000. Oh, all right. So we're starting to see this happening now. All right. So we know that at some point at like 8,000-ish, this started to head back down again. We clearly need this to be larger. The Y max we can send off to like, I don't know, it's got to be in the millions now. Needs to be higher, but we're getting there. Really getting there. 1,750,000. Okay. I want you to notice what just happened there. I, your math teacher, sometimes struggle with finding the correct graphing window. So it does not surprise me at all when students are like, I have no idea how to find the correct graphing window. You have to first just use the information that you have. I was erroneously using the fact that I was getting a profit of $200 and $300 per stereo as my max profit. So that was my first mistake. But other than that, it's really just kind of trial and error and seeing what does and doesn't work. You know that at some point after you hit 4,000 stereos, something starts to decrease at some point, and you don't know where it is. Well, what we can do here is we've graphed the profit function. Now you can kind of see the whole thing. I know the light's not the best. Sorry, I really should get the emulator going, but then I have to take the notes away. And I think it expired. I'll have to work on that. Can I make this any better? No. Okay, so what we can do here is you can go to second calculate. I think we have done this before, but I cannot remember. Hit number 4 for maximum. And remember, this is your profit function. My cursor is showing up over here. I don't want it over there. It's going to ask you for a left bound. Scroll to the left so that you're somewhere to the left of the max. And then hit enter. And then it's going to ask you for a right bound, and you're going to scroll over to the right. So you're just somewhere to the right of the max. And hit enter. And then it's going to say guess, and you're going to hit enter again. Trying to make this look better. Why? Okay, and it's going to give you a maximum value of approximately X equals 7,500 and Y equals 1,587,500. Graph the profit function. I'm just going to do like a quick sketch of what we just found, and I'm going to write out what my window is in, but it kind of looks something like this. obviously the scale is going to be, oh, I'm going to, instead of calling this y, I'm going to call it p of x and then x. All right, so this is your profit function. It's maximized at approximately x equals 7,500 and y equals 1,587,500. So that would be x and p of x. Now, there's another way of doing this that we're going to be using in the next chapter, and I'm going to show you real quick. First of all, I want to write my window down here. So my window for this graph, which I found by trial and error, unfortunately, that's kind of the way it is when you aren't using applications of the derivative. For your x, you're using 0, and I had mine at 19,000. It doesn't have to be that high. And then for your y, it's going from, I had mine at negative 100. I don't think that really matters, but sometimes I like to see a little bit under the axis. And then 1,000,000, trying to make my commas distinct here, 750,000 for the minimum and the max. Okay, so that was how I set my window, and this is what we found for maximizing the profit. Okay, in the next chapter, we're really going to be focusing on how to find these maximum and minimum values just by looking at where the slope of the tangent line to the graph is equal to 0. So let's say we did that. If we took p prime and we set it equal to 0, what you would find, like p prime is up here, is we have negative 0.06x plus 450 equals 0. And that leads you to 0.06x equals 450. And then when you take 450 and you divide it by 0.06, you get x equals 7,500, which is a lot faster than trying to do this trial and error. Now, it's really important that we can see this on the graph, that we understand what it represents and where it comes from. But the whole idea is if you can figure out where the slope of your curve is 0, then you can just find the corresponding y value at that point to, in this case, maximize your profit. So if I find now the profit of $7,500, you're just evaluating that profit function. I mean, we have the profit function in our calculator. You could always just evaluate it. Yes, that is the profit function in your table, 7,500. And that would give you the same value we came up with. Now, it gives you 1.59 times 10 to the 6th power, but it writes this down here as 1,587,500. So I always scroll over it, or I hover over it, and then I get the full value down here. So that means the profit is maximized. Max profit is 1,587,500, and that occurs when 7,500 stereos are produced. Okay. So that was marginal and average cost. We talked about how to find the cost of making one additional item. We talked about the revenue and the profit when one additional item is produced. We talked about average cost, revenue, profit. So you kind of understand the terminology now and the keywords that are involved, and hopefully that will guide you along as you work your way through your homework. Sorry, I was a little off today, but it'll be better next time. Have a wonderful rest of your day. Enjoy working on your marginal functions.